you'll do an introduction, will you?
Yes, I will quickly introduce you. Okay, we're live. Thanks everyone for joining our session. We have with us Roy Brooks, Jose, Manuel Dominguez, and also we have Rebecca Arista. This is our industrial demonstration session. We have the presentation here. Now we'll leave the floor to Roy, and if you have any question, you can write it in the chat. We will address everything after the presentation. Thank you.
Oh, okay. Thank you, Luigi. Well, hello and good afternoon or good evening, good morning, wherever you happen to be, Onto Commons members. At first, my thanks to Emilio Sanfilippo for suggesting we participate. I think we're a little outside the regular remit for Onto Commons. And then also to Arco Sarkar, thank you for the opportunity to introduce Circular. And also share our particular challenge with your members. Before I get into our presentation, just a couple of caveats. I'll probably spend a little longer than most speakers introducing Circular for a couple of reasons. Well, one, we're a new project, and I'd be extremely surprised if anybody listening knew anything about us or had heard about us. Secondly, we're in a rapidly developing but new field that is alternative to plastic materials. And then perhaps most importantly for this conversation, and as will become abundantly clear, I'm sure, as I continue, I am completely ignorant of ontologies. It's not my area of expertise by any stretch of the imagination. But as a systems director for Circular, it is increasingly becoming part of my responsibility. So I hope you'll bear with me. But I mean, all that having been said, hopefully the next half hour will be worthwhile. We think our challenge is something in a new area, and we think it has possible potential for innovations in your particular discipline. So I hope that's all coming across fairly clearly, and I'll pop into the presentation. I'm going to try screen sharing, and hopefully you will see a title that says Alternative to Plastic Materials, a New Ontology. That's probably an extremely large claim in this context, but we needed a title, so this is as good a title as we could come up with in the short time. So, okay, but I think a little bit of background. Inevitably, the question is going to be, what is Circular? And I'll put some words in place. Circular, it's an integrated platform providing access to materials, expertise, and tools to support the circular post-plastic economy. Wow, okay, that's a lot of words and a complicated diagram. So what I'll do is I'll just briefly unpack those for you. So platform, well, in this day and age, we all know what platforms are: integrated suite of utilities, functions, facilities, or whatever, to provide people access through the web. Depending on what it is, think Uber, think Facebook, think whatever. That's where we are. We are a platform. Circular. What do we mean by circular? Well, I think again in this day and age we're all fairly familiar with the concept of a circular economy, that is using resources in a cyclical way as opposed to the predominating approach to production these days, which is still essentially linear. So really out of a mine, into a factory, ultimately into a dump, and you losing all its. Whereas circularity involves, broadly speaking, from field to factory, through retail and so on, and back into the field again. Nothing particularly. So that's the domain we're working in. And then post-plastic. Now, post-plastic is a bit of a catch-all term but essentially we use it to mean replacing fossil-based polymers, so plastic, with organic equivalents. So let me put that into some sort of context. Why does circular exist? Well, I think again, one of the things that we're all very aware of in this day and age is that plastic poses an existential threat to the planet. Just some stats around that. 99% of plastic is currently made of petrochemicals. And as we all know, that is toxic and it leaches and appears in pretty much all of our ecosystem. In fact, I think, I may be wrong, but I think plastic has been found in space as well. So it's also a hazard to us, animals, and the ecosystem in general. It also produces roughly about 850 million tons of CO2 just in the production and disposal of plastic. So when we talk about global warming, plastic and production of plastic is a significant contributor to that. Sadly, plastic production continues at unsustainable levels. It is a wonder material. It has extraordinary uses. 460 million tons are produced annually, and about 440 million tons of that goes to waste. So a tiny, tiny amount of plastic is recovered and reused. And it's not slowing down. By 2034, estimates are that plastic production globally, so that's fossil plastic, will roughly double. And of course, investment goes along with that. So about 400 billion investment in plastic in the USA alone. So that's just the USA, that excludes Saudi Arabia and so on and so forth. So it's a big issue. Now, I'm sure we're all familiar with recycling, and recycling is currently one of the potential answers or solutions for petrochemical-based plastics. So let's just do a quick look at that. Is it the answer? Well, almost as much plastic waste as virgin plastic, in other words, plastic that literally comes straight off the production plant, is produced each year. So it's about 400, roughly 450 million tons of feedstock are available to the petrochemical plastic industry. Now, recycling has been mainstream and it's been front of mind increasingly for quite some time, I mean decades. But currently, roughly speaking, only 10% of all the plastic ever made has actually been recycled, despite all that work and all that effort in consumer awareness, business development, and so on and so forth. Now, yes, it can be recycled. Plastic can be recycled, but it is an ongoing degrading process. So recycling degrades it to a point where it actually can't be recycled or used economically. So it essentially has to be either buried, dumped, or burned. Then there's chemical recycling. And chemical recycling can convert plastics back to oil. But at the moment and for the foreseeable future, it's highly energy intensive and its benefits are somewhat debatable. I mean, that may change with changing technologies, but that's the current state of the market, as it were. The bottom line is that plastic will always become a pollutant unless it's actually isolated from the environment. That is just part of its nature. So we're in alternative materials. So let's have a look at, can we turn to alternative materials? Well, crop waste alone, so that's just the residue around the world from growing food, 3.7 billion tons available. That's 10 times the total amount of plastic produced. There's a huge amount of potential in this. Current alternative materials can technically replace around 70% of petrochemical plastics. So that's that the technology can produce a product or a material which is broadly equivalent to a petrochemical plastic. Bio-based materials, of course, particularly those produced from waste, which is primarily where we're focused, these consume less energy. It's that simple. Using alternative materials for all the above reasons reduces the impact on climate. So, and also the waste of burning, burying, and so on and so forth of existing waste materials. They're also safer. Again, I don't think I need to elaborate on that. There are fundamental differences between bio-based polymers and fossil-based polymers, fossil oil-based polymers. And I suppose, last but not least, by any stretch of the imagination, this industry, or this nascent industry, represents an enormous opportunity for businesses. I mean, currently, roughly 6 billion market. It's 1% of the plastics industry. So there's real potential there for a growing economy. Okay, so yes, moving to bio-based alternatives is a real option. But there's one fundamental problem, and this is really what has brought Circular into being. It's a bit like the computer industry in the 1980s. It is comprised of a few large initiatives, principally in the chemicals industry, but for materials in general, it is fragmented. It's small. There's no supply chain. It is a nascent industry, but for this discussion, perhaps the most significant aspect of it is, like any domain information, it has almost no common language. Now, I hope you'll excuse my use of the term language. It's a layman's term. Again, I'm using it as a shorthand, as a catch-all for the purposes of this discussion. So that is what Circular has set out to address. So what is our solution? I've said we're a platform. And our approach is initially, and this is where we are currently, is to inform. So that is to provide data in various ways and formats to enable manufacturers, designers, brands, and so on, make the switch from plastics to alternative materials. And as a component of that is also collaboration. So platform, one of the great functions of platforms is to be able to share knowledge, again, in many forms. So that's another aspect of the Circular platform. And then to enable transition, and that's a very key element of what we're trying to do, is because transition is possible, but it requires knowledge, investment, engineering, and so on and so forth. So again, that is something that we're looking to support. And then as things grow, of course, scale. So again, I don't think I need to go into detail on this, but scale is critical in an industry which is looking to challenge. And then I suppose, perhaps more particularly, the concept of protecting, the concept of everything that we're looking to do is essentially based on data, sharing knowledge, material information, production data, production functions, and so on and so forth. All of that needs to be in a protected conduit, in a protected pipe that maintains the value of intellectual property that's wrapped up in it, but also the security of production, and so on and so forth. So it's that's a pretty big remit for a startup project, but I'll leave that there for the moment. So one thing that it does do, and I've just touched on that, of course, the topology that I've just outlined, of course, suggests a myriad of data touch points. Now, this is an incredibly simplified diagram, but it does touch upon some of these. So we have essentially two streams. You have the materials coming off farms, be it farm waste, be it farm products, through what we would say is the sort of the agri-waste stream, with all the various data collection points and data exchange points that exist in that trail, through retail, and then finally back into the earth, full circularity. But also because at the moment we are very much in a transitional phase, or we're at the start of a transitional phase. So of course, there's still going to be in this supply chain a considerable amount of plastic waste. Recycle it. So again, addressing that from the standpoint of circularity, as opposed to the current linear model, expecting it to end up in a dump or be burned, is to say no. With data, with the use of data, with tracking, with managing production and so on, you can have an approach, a circular approach to handling recyclate, which over time will hopefully diminish in volume compared to non-fossil based plastics. I mean, as I say, it is a very, very simplistic diagram. So, okay, that's hopefully a brief overview of what Circular is, what we're about, why we exist. So here's the question: why is Circular presenting to Onto Commons? Well, we've started a journey, and in the process of this journey, we have come up against a challenge, a significant for us, and we think for the industry challenge. It's a real world challenge, and that we think an ontology. And again, I hope you'll excuse my layman's ignorance of your discipline, but we think, having had some discussions with some of your colleagues, that this may be something that is worth looking at. If you think in broad terms of what I've just described, and in the most broad terms, a platform like Circular is going to have to interact with a vast range of domains, all of which have their own languages, have their own ways of approaching their business models, have their own ways of handling their data, and so on and so forth. But for a fully functional supply chain of the kind that we envisage, we at the center, and others at the center, because, I mean, of course, as you can well imagine, Circular in no way will be able to build out the entire model that I've illustrated. That can only be done with partners, and that's very much our approach to business. But in a general sense, these are some of the sorts of areas that the ecosystem will have to comprise, and information data will have to flow across those domains. So having a common, again, I use this term advisedly, language is going to be absolutely critical. Now, when we started, we thought in our ignorance that essentially what we needed for our core database would be a taxonomy of materials, material specifications, and so on, everything relating to those materials. But when we considered it in a broader scale, as we're doing here, it quickly became apparent that to integrate all the domains we're addressing, agriculture, materials, manufacturing, IoT, we needed to think much more broadly. We needed to think much more conceptually. We needed a holistic framework, and I say, again, advisedly, a holistic language framework to integrate all of these, or at least to give us a chance of integrating these. And it was at this point that we started looking at, all right, where might this come from? And it was at that stage that ontology came to the surface, and we started investigating it. Now, just to illustrate this in a very specific way, you'll have noticed that at the core of everything that I've shown you so far is the data hub. Is this again? See it as a virtual data repository, whatever its ultimate physical structure is. But simply to achieve our first level aims and ambitions, which is to inform people and to facilitate the transition, there is a huge amount of data that is going to have to be exchanged and also consolidated. So let's take, for example, one of our core products is an alternative materials library, which allows people to discover alternative materials. That is going to require standard taxonomy, just a huge range of attributes that make it usable. Similarly, if we go to an alternative material selector, which we ultimately envisage as being an AI-enabled rapid selector, exactly the same thing. And being informed in this way, of course, that raises the number of data points, access to data handling, and so on and so forth exponentially. So that's just one small aspect of what we're actually looking towards. So, excuse me for a second. Okay, now coming to what we understand about the challenge of ontologies or implementing an ontologies. we know from some of the research we've been doing into this that established industries face challenges when they're implementing and using ontologies. And some of these: fragmentation, knowledge alignment, expressivity. You can read all of these. I mean, these are coming to me as new, but I'm sure you're all familiar with them. And I know that quite a lot of the sessions in this workshop will be looking at these various challenges. But I just want to put that in context with the domain that I'm working in and in terms of its development. I mean, by comparison, you have several decades of industry engagement, academic engagement, thinking about this. In the space that we are, there's almost nothing. It literally is a blank space. It is highly fragmented. It's experiencing rapid, uncontrolled knowledge growth. There is a complete lack of common terms. There are no established standards. Tools are still in development. It's what the alternative materials industry offers to brands, production, whatever, is pretty alien to most of them. Most of the solutions that are coming up are hermetic. They are unique. They don't exist within a broader framework. And there's barely any data models, or at least common data models. So it's a pretty large challenge. However, we're positive. We think that a blank space is also a blank canvas. So it's an opportunity to use technology to accelerate a network, use technology in a way that the industries that we are looking to challenge actually have passed. But we can take advantage of that. An opportunity to capture knowledge in a structured way from the beginning. So to develop common terms early, to establish standards early, or at least to establish mechanisms for handling standards, because we recognize that, of course, standards are a whole question themselves. Create tools that are appropriate for the new domain and materials that we're working with. Co-develop as opposed to developing in silos. So with industry innovators, Industry 4, Industry 5 innovators. Provide a basis for commonality of development. Again, a foundational, but build a flexible, appropriate data models. So we don't have to retrofit at the cost of retrofitting to existing circumstances, but rather use this as an opportunity, not necessarily to start from ground zero, but at least to be able to think towards the future or design towards the future with the history in mind. So, I think that's pretty much, that's me. I think probably about 25 minutes in. I just want to sort of almost end this with just a quick illustration of one of the reasons why we think what we're doing is worthwhile. Just within environmental returns. Again, I'm not going to go into this in great detail. You can read it, but reduced emissions. Waste that is currently burned or buried becomes actually a valuable resource for the people who produce it. Diminishing pollution. There's a whole and ever expanding upside to actually having an integrated, comprehensive supply channel for alternative materials. So, I think that really, in summary, petrochemical-based plastics pose an existential threat to the planet. I think we can agree on that. Alternative to plastic materials offer a real solution. They are something well worth considering. They have great potential. A lack of common language is a very fundamental, we think, barrier to their use, but it's an opportunity to build a strong foundation and accelerate the adoption to all our benefits. Thank you. Over to you, Louis.
Thank you, Roy. That was very insightful. Yes, indeed, we see across this event that when a new technology is developed, it's very likely that ontology will help. All right. So thank you again, Roy. That was very interesting. Now I will leave the floor to Josep for your presentation. Thank you.
Thanks, Dimitri.
Thank you, Luigi. So I will start sharing my screen. Should be this window. Is it working? Do you see the presentation, Luigi? I hope so. If not, just interrupt me and if something is not working. Well,
Yeah.
so my presentation, thank you. My presentation is about software product, actually, so eminently technical. It's about, it's called Symphony, which is a software that we developed at the Fraunhofer IWM. And the aim of this software is to achieve interoperability between software products using knowledge graphs as a common language. So essentially applying all this knowledge organized in ontologies. This it's in the form of a Python framework, and it's open source. So in particular, it has a BSD3 license. So you are even free to build up on it in basically any way you want. It has very little restrictions. So and to go into a little bit more detail, I'll split the presentation, let's say, into two aspects, so it's easier to understand everything. The first one is the fact that in order to work with the knowledge graphs, even before we get to the aspect of the software interoperability, the package needs to be able to offer you a Python interface to ontologies. So this is one of the of its functions. It's not its main focus. So I will come back later to this point, actually. So, but we need to have this, and then after it is clear what it offers in terms of manipulating or exploring the ontologies and building knowledge graphs based on them, then we can go to the interoperability aspects and how this interacts with third-party software. So as said, I will start with with this aspect of being a Python interface to ontologies. And even before starting, I want to make a remark. Essentially, I mean, there's a typical way to categorize the knowledge contained in ontologies is as follows. So you define one category, which is terminological knowledge, or T-box typically called. I mean, here you aggregate all the classes, relationships, attributes, and annotation definitions, and the axioms that affect them. And then you have another category, which is called the assertional knowledge, that refers to actual instances of these classes, the so-called ontology individuals, and the actual relationships between them and the values of their attributes. This distinction is important in this case because in the most important point, or to clear up some confusion that is or people usually manifest, is that Symphony, the terminological knowledge, so the classes and relationships and attributes and so on, is read-only. So this is, I mean, you prepare an ontology file and then you install this to Symphony. So you make it available to it. So to create the ontology itself, I mean, the terminological knowledge, you can use any other well-established tools like Protege is very well known, or I mean, even already, because often many people ask me what's the difference with already and this software. So yeah, I mean, when it comes to creating the ontology file to be used, you can use any of other tools, and then what you do with Symphony is actually creating, editing, and querying the assertional knowledge, so the ontology individuals, let's say. So the actual when you want to build data based on this terminological knowledge. Well, having said that, then in Symfony you can install all ontologies and RDFS vocabularies, but the actual internal model in Symfony is all ontologies. So if you use an RDFS vocabulary, you will kind of work with it like as if it was an all ontology. It's kind of mapped. So I mean, the classes can be mapped to classes, but if you know about RDFS vocabularies, the relationships, they are called properties, and the actual correct mapping is an annotation property in O. So yeah, just for you. So the internal model is O. That's the important thing to keep in mind. Then Symfony is, I mean, it's the data structure that is underlying it is basically an RDF graph. So it's fully RDF compatible. I mean, this is no special standard or anything. And an important detail is that the only special thing we have, let's say, is that there is an additional feature to actually mix the knowledge graphs with raw files, because I've seen commonly the need, for example, even in our material science domain, to have a picture, for example, of how a material is breaking. Then it's useful to run some machine learning models, for example, on this to say, okay, I automatically identify the fracture and then add some metadata to the picture. But then you want to store both this metadata and the picture together. I mean, that's a requirement typically that research groups have. So that's why we also thought about this direction of allowing this. Well, now I will very quickly walk through an example, I mean, of how this looks when actually using it. It's super simple, but hopefully this makes the topic less abstract. So in the example, what is done basically is from the a set of installed ontologies that we have added to Symfony, we import a so-called namespace object that is used to retrieve the entities from the ontology. And then from this namespace object, we retrieve precisely an ontology class and then create several ontology individuals. So in particular, this example, I mean, the exercise to solve is to represent a tritium nucleus using the European multi-perspective materials ontology and save this to a Turtle file. So let's see this. I mean, the first step would be to make sure that we have the ontology installed into Symfony. For that, there is a tool called Pico, which is the ontology manager of Symfony, let's say. So using this, you can list what is installed, as you see on the left-hand side, and then you can run the install command, and using that, you can install the ontologies. In this case, the emo ontology is sort of included with Symfony, or rather a pointer to the ontology file on the official site, so it's even easier to install it. Then after you do that, then you can go to a Python shell and actually use Symfony. So as said before, you import a namespace object, and then you can use this to access the ontology classes. So I mean, this is a namespace object. Then using the dot, you request an ontology class, and then later you are using this to call the class. So what you have at the end, so the result of the whole operation is the ontology individual, and this is what is going into this variable here. So the same story as is done with the nucleus here is done with the proton and the two neutrons that we need, and then we use a relationship from the emo to hash_part to connect the nucleus to the proton and the neutrons. So the outcome is actually what we wanted. So what you see here, it's a I mean, there is a tool in Symphony to create a graphical representation of the A box that was created, the ontology individuals, and then we can get this picture. So the only remaining part would be, I mean, this is also to emphasize the RDF compatibility that would be to export what we created to an RDF file. So for this, there is also a tool in Symphony, this export file function, and you can choose what to export. What file do you want it, what format, and then you get the RDF representation of the of this assertional knowledge. And also, I wanted to emphasize that because the most common operation that actually you can expect to perform, I mean, apart from creating terminological knowledge, is obviously accessing it. So I wanted to emphasize that there are several ways to do it. And for example, one is even direct Sparkle queries. And what you see here in this example is basically how I'm looking for nucleons that are part of a nucleus, but written in Sparkle. And if I run the query, I also get the ontology individuals that I just created. So if you look, I mean, this is a shortcut for the IRI of the individual. And if you look at the previous picture, then they match. Those are actually the neutrons and the proton. This is everything that comes to the Python interface to ontologies, and then once it is clear how to operate with it, then it's easier to understand how the interoperability with other software products works. So, I mean, what the design to achieve this is a 3-layer design. So on the top, you can think of, I mean, there is Symphony and the user that interacts with it. So, I mean, the things that we were doing before in the previous example, that's direct interaction with Symphony. That's the top layer. And then there is a middle layer called the interoperability layer, where there are the so-called wrappers that are like plugins to Symphony that consist of, I mean, this is something that a developer has to write, and using an API that is defined by us, you implement a few methods, and then you can essentially translate the language that is spoken, let's say, in the inner layer of Symphony, which in the end I said it's based on RDF but also supports files, into the backend specific commands actually that are what the software products are using. So I mean, in the end, things will translate to inserting data into a table in a database, or setting up a simulation in a simulation engine, or exchanging some HTTP data with a data repository, or whatever. So that's from the technical point of view, but from the actual user point of view, the interaction with each software product is abstracted as a so-called session object that you can see as a box where you can put ontology individuals, so assertional knowledge. So this picture is meant to represent that. So in here, this cloud here represents this so-called session object. So in the example that you see here, what is represented is how you have some atoms stored in an SQLite database, and then using the adequate Symphony wrapper, you see this as a session object, and then you can essentially take your atoms and copy them into a different session from the LAMPS wrapper. And then there is a command that you run. So you ask LAMPS to run your simulation, and then it changes the velocities and position of the atoms. And then you can do whatever you need with this data, like, for example, putting it into another session into a graph database. Or, I mean, you could also put it back to a SQLite database, whatever. I mean, the important message here is you can take your ontology individuals, move them around to the different sessions. That's how you transfer the information between the software products. And then for the simulation engines, there's also a command so that you can run your simulation and change the state of the objects. And yeah, when I mean, I would say that's one of our weakest points at the moment, unfortunately, because I quickly summarize some wrappers for Symphony. So as mentioned, there is this SQLite wrapper, which is included with Symphony. So let's say I put a check mark that this is included, so you don't even have to install it. There's also an SQL Alchemy wrapper. Actually, the SQLite one is based on this one before you make the question. But just for simplicity, they were split. Then there is also a very simple wrapper called data space wrapper that is actually based on the SQLite one, but it demonstrates how to actually Symphony mixes the files and knowledge graphs. I mean, I can even show you an example later if you are interested. And then there is this one is also included. And then there is this remote wrapper, which serves to, you can open a wrapper in any server, then you can use this to connect to it. So let's say that you can not only work locally, but also remotely. And then this example, this wrapper Symlamps is used in the, has not only been used in the picture before, but it's also used in the as an example in the Symphony documentation. It's a very simple implementation. It doesn't support all the functionalities of Symlamp of lamps. And also I need to make the repository public still in GitHub. Sorry for that, but yeah. And this one is not included. And then, in the Fraunhofer IWM, we actually have around 20 wrappers more, but I'm not promoting them for you to use, essentially because, they are not, let's say, so publicly production ready to say, so they support sometimes only specific applications for specific projects. And the most important reason is this one, so that most of them are not open source, not commercial yet, so we just have them for internal use. But just to let you know that it's widely used in our projects. And this takes us to the end. So the 2 points that say that or the takeaway message from this presentation would be to make you aware that Symphony exists, and the aim is to achieve interoperability between software using the knowledge graphs as a common language. So you see that the session for the abstraction for the software. The abstraction for the software is are those session objects where you can have ontology individuals, and then you can move the information around using them. And what is contained in the sessions are the knowledge graphs, essentially based on all ontologies. And second, you have a Python interface to these knowledge graphs in order to operate with them, but with the particularity that the terminological knowledge is read-only. So it focuses on the actual data or instances based on this knowledge that you have designed beforehand. Here you have a link to the documentation where you can find all the details. Here to the PyPy project page where you can, you could download it using pip, or from here you have further links to the GitHub repository and such. And then this is a mail address that we have, so that you can directly contact us if you have questions or suggestions, or want to know more, or maybe you found the approach interesting and can use a wrapper in your project, whatever. Just let us know. And lastly, what I'm presenting you today, this is an important remark. It's still in release candidate state. Because it is the next major version of Symphony, which is the version 4. Previously there was a version 3. But this one is much more usable, so I decided to present it to you already, even if it's a release candidate. So you will find, for example, that the documentation of how to develop your own wrapper is still missing in this page. So you would have to wait a while for this. But hopefully today you could, with this presentation, you have been able to understand the concept and familiarize with yourself with it. Hopefully it's useful for some of you. Thank you for your time and attention.
Thank you, Josep. That was a very interesting hands-on presentation, a nice tool. Now I'll leave the floor to Rebecca. I see Arco there. Hi, whenever you're ready.
Just one question that Roy Brook, did he present?
Yeah.
Excellent, excellent. Okay, so it is only.
So I could combine. This one better. Yes. I need to share the screen. Yes. Okay, can you see it? Yes. Is it? Yeah. Okay. So good afternoon. So thank you for joining this presentation. So I'm Rebecca Arista. I'm an industrial ontologist and knowledge engineer at Airbus. And I will present today the work that we have done in a European project that is called Quality. And so we did that in collaboration with EPFL, Fraunhofer, and Visual Components. So this European project is quite representative of the use of ontologies that we do inside Airbus. So whatever you see here, it's something like extrapolated from the problems that we are dealing with inside the company. And the aim of this project was to have a trade space framework for autonomous quality manufacturing system design. So how to design our manufacturing systems considering autonomous quality from the very beginning. So first I will start with the Airbus vision on this sense. So what is the future of manufacturing engineering? Then how this pilot was covering part of that vision. And then I will guide you through the details of the prototype that we have built. So first of all, so what is Airbus' vision of the future of manufacturing? So we're aiming at 4 different pillars. So the first one is operator-centric. So in the production system, so we're trying to focus on where the value is created. So right now the aerospace industry is still very much based on operators. So we have low automation because of different constraints of the industry. So what we want is that the operators have every information and things that they need so that they can create value more quickly. Right? So the second point is the operational excellence. So we want that all our operational Airbus operational system can bring the most out of the production system so that we can ramp up our products more quickly, we can deliver more quickly and with more quality. And the third pillar is the industrial system design. So to make sure that during operations we can bring the most excellence, we need to consider a lot of things from design. So this industrial system design that includes every digitalization option that we can consider that will be later used in the operational system. So this is our third pillar. And fourth is the co-design. So how do we design with a product, production system and services system at the same time and consider that the constraints that the product will put to the industrial system or the services system will have an impact, and the other way around. So constraint from the beginning, industrial system requirements that we need, that are coming more into play, like emissions, CO2 emissions of our industry and these kind of things, the footprint that we bring that into the co-design process with our products. So in order to do that, we have 3 main streams of activity, let's say. So a workplace design. So we're more into the design of this workplace around the operator and around the, improving all of our processes. So the design of the the workspaces are more suitable to bring more excellency. Then digital continuity, of course, and on that point I will come. So how we apply ontologies on that sense to support us, and then third of automation. So in all of these 4 steps, wherever we can bring automation and capitalize the knowledge that we have collected since many years. So that's another thing that we're checking. So on that matter, quality project. So quality project is a European project. So that's the full name. It has lasted for 39 months. It just ended last July. We were in total 45 partners, European partners from 13 different countries in Europe. And it was a 19 million euro project. It was big figures. So we were 14 pilots dealing with different phases of the product life cycle. So from engineering phase, so from the design, then the procurement stage when we are putting up the system, then the manufacturing stage, so everything that it was IoT connectivity in the shop floor, and then the sales and services, so the servitization of the manufacturing system. So you see there were different industries, so from like the goods like Whirlpool, Philips, Siemens, Continental were different pilots. And our pilot here was focusing on the engineering phase. So how do we check quality by design? So we imposed quality standards by design. So our goal was to enable an MBSE and a collaborative design process. So between the aircraft and the industrial system domains, with 3 main problems to solve. So knowledge management, interoperability, and decision making in this process of co-design. Okay. The use case that we used was the aircraft fuselage orbital joint process. So it's one of our key processes in many of our lines. And the objective was to have a framework, a prototype framework of this trade space that could enable trade-offs so that the architects can trade between different options of how to build this orbital joint process. So for those that doesn't know what an orbital junction is, so here it's a picture of how it looks. So this is two parts of the fuselage of the aircraft. So this is the front part and the rear part. I think this should be like the A350 that you took to come here because of the size. So the orbital joint process consists of putting these 2 pieces together. Okay, we have at different sections of the fuselage, the same cut, and we have to put the stringers into line. We have to put the frame into line, the floor, and you see that we have a lot of accessibility problems around this process. And while this process is ongoing in our final assembly line or pre-lines, all the other processes are stopped. So this is part of our so this is a main process that we do in order of our lines. So to give you an overview in a nutshell of what were the results already of these pilots. This is not the one. So this video compiles the results and has important messages from top management about what are our targets and how this was complying to the target. Okay. In the web, do you listen to the audio if I put it on? Yeah. I hope.
For the moment, we don't hear. Actually, if you share the screen, there is a toggle that says whether you are sharing a video. Maybe try that.
Share.
See at the bottom, when it asks for screen and PDF, there is at the bottom a toggle for the video.
The system. Okay. It's clear. Okay.
Imagine yourself
Yeah.
in
Now we hear, yeah.
charge of designing a bridge. Right from calculating the various loads, you'll have to investigate different forms of bridges, estimate the forces of nature, select appropriate structural materials, and so on. You'll need to make numerous design choices for the safety and longevity of the bridge before you finalize the design that is the strongest, lightest, and most economical. In fact, bridges and aircraft both follow the strict laws of physics and the forces of nature as beautiful feats of engineering. Now can you imagine what it will take to build an aircraft?
The co-architecture of an aircraft and industrial system means to have in mind all aspects of making the industrial system the most economic sustainable, the most environmental sustainable, and the most social sustainable system, people in mind. But that means also that it needs to be resilient, and an important aspect of all that is the first time right way of working. In other words, zero defect manufacturing. And this is all about this project. Having in the early phases already all the stakeholders together and setting it up in a way supported by digital means that we can make decisions, the right trades between the various impact of the processes, the technologies, the right sequences, keeping in mind the logistic flows, but also having the right level of automation planned in order to come up with a result which is indeed zero defect and first time right.
Current design processes and digital solutions do not support this approach efficiently enough. Aircraft design and manufacturing system design are not fully integrated, which sometimes leads to quality issues being discovered late in the production process, meaning time-consuming revisions and additional costs.
Quality Project aims to demonstrate how European industry can improve its competitiveness advantage and meet Industry 4.0 targets by building unique zero-defect manufacturing strategies with orchestrated open platforms and digital enablers across all lifecycle phases. The objective of Airbus Pilot in Quality Project is to have a trade space framework for autonomous quality manufacturing systems design, using MBSE method and semantic web technologies. This framework will help engineers to explore all design possibilities in collaboration with all product and manufacturing domains, overcoming bottlenecks of knowledge management, interoperability, and decision-making.
First, existing documents and information from the current assembly processes are collected, collating existing knowledge through ontology-based solutions. The engineer's knowledge of how they design the assembly process is also included, describing the rules and constraints they follow. With that, the system is ready to support a new assembly process design. A new design starts by receiving an aircraft concept and defining performance targets that the engineer wants the manufacturing system to achieve, like the number of aircraft produced per year and the level of automation in the assembly process. This triggers generative design algorithms, which use the knowledge captured in the trade space framework and propose to the engineer all possible assembly process designs that could fulfill the performance targets. The engineer can then trigger the automatic generation of several simulation models and simulate the assembly process to verify whether or not it will fulfill the performance targets. Any of the assembly process options can be verified in a 3D context to confirm expectations and quality. The process described results in a manufacturing system design that best meets the requirements set. The easy reconfiguration of the manufacturing process will be compliant with autonomous quality concepts.
Three of the most important points related to industrial architecture are the definition of interfaces, the consistency of how we define our figures of merit, and the automation, or actually the consideration of as large a design space as possible. What quality is doing with these regards is that it's standardizing our interfaces so that they are pre-defined and or reusable. It's giving us a good repeatability for our processes, and additionally, it's giving us a way to automate the boring parts of assessing all of the options that are resulting from our requirements in an automated manner.
The model-based systems engineering methods, together with the trade-based framework, are a good foundation for us towards the modern way of working for achieving a zero-defect manufacturing system. We also have seen that we have, with these new technologies, a good opportunity of learning of state-of-the-art processes, and are able to take this as a stepstone to our future developments of future aircraft.
Okay. So coming back to the slide, so now that you have a good overview what the pilot is, so we can go into the prototype details and the technology value of what we have demonstrated on this framework. So first of all, the motto that we shared in the pilot was that ontology is the tool that we use to capture and represent knowledge and the meaning of data. And with that, we want to support this design process and capitalize on this knowledge and existing data. So in order to do this prototype, we followed as well an MBSE approach. So we wanted to have first an authoritative source of truth. So we wanted to have an ontology that is used to represent the assembly process and the virtual models across all the life cycle. We wanted as well to have requirements that are defined for the user needs in the end users of the industrial system. So what are the performance requirements that this system will need to consider? So build architecture model. So use semantic MBSE to implement an MBSE method that is called, well, in Airbus MOFLT, so mission, operation, functional, logical, physical architecture of the industrial system based on our application ontology. Then we want to verify our architecture by running 2D simulation models, so discrete event simulations to check the performance evaluation, and then 3D simulation to verify clashes, constraints, and optimize the different manufacturing alternatives. Okay. All of that to support trade-offs between the different options that the architects had in front at the co-design phase, okay, when they discuss with the product architect. So in order to do that, we define these functions of the prototype. So define and manage requirements. I have a requirement traceability. Both of them will be managed by a requirement management block and a system integration block that I will detail later on. Then we want to define the industrial system architecture alternatives and define a trade space exploration. So having what is the range of these parameters that we're going to play around with, and what is the design of experiments that the architect want to assess. So all of them are covered by the architecture definition block. Then we want, of course, to perform trade space exploration. So have a Pareto analysis, surface graphs, and yes, a way to analyze the results. So that will be covered by the execution of the verification block and the visualization of the visualization block. And use surrogate modeling to perform also sensitivity analysis. So that will be done by two different types of models that I mentioned before, discrete event simulations and 3D assembly simulations. And then we want to integrate our models in a co-simulation process and transform between different modeling language that we'll be using in different steps. So that will be supported by the visualization block and the verification block. And of course, have a tool agnostic industrial design process so that everything that we do in this prototype is transferable to another toolset choice, and that we use ontologies for reasoning and decision making in this prototype. Okay, so with that, all of these blocks came into play into this functional architecture. So we had a front end and a back end. The front end, it was just the requirement management, the architecture definition and visualization, interfacing with two different roles. An engineer that is in charge of defining target requirements for the manufacturing system and checking that the options are compliant to these requirements, and an architect checking the architecture definition and running the simulations. Okay? All of that supported in the backend through a system integration block and a verification block that will run the surrogate models.
You have all these engineers. Some of them are design engineers, some of them are manufacturing.
Yes, but here we're focusing on manufacturing engineers.
So isn't the requirement side design?
So we split manufacturing engineering in manufacturing engineers, what's understood commonly, and architects who have a new MBSE view of the manufacturing system in order to check performance of the system towards the performance of the product system. So we have these two roles that are now.
So all these are manufacturing.
All of these are manufacturing.
Okay.
Yeah. So then, starting from the backend, so the semantic integration block. So in order to understand this block, first we need to see the tool chain. So the requirement management block was supported by a solution that is called OnRack that will be connected to the middleware to the semantic integration block. The architecture definition was supported by MetaGraph. Same with the middleware, we have a connection with the semantic integration. Verification, discrete event simulations were run in Symphony, and 3D simulation and visual components. And then the visualization, well, it was using different commercial solutions. So we have a knowledge graph database that we were using Neo4j for this prototype. And we have different, well, we had a cloud server to have these API calls for the connectivity to the other systems. And so we have, so the system integration was provided input and output for all the blocks. So it was ensuring the data flow and the continuity between all the flows of the team. And it was receiving as well feedback, so the data, collecting data from all of these blocks.
So when you say requirement here, is it design requirement or manufacturing requirement?
Both. So it's a design requirement that impact the manufacturing system, and manufacturing system requirements like a rate, for example. So produce 150 aircrafts per year. And so that is an industrial requirement.
How about manufacturing capability? Requirements like you need to be able to, handle the size of the fuselage, for example. All those things.
Yeah. We use them as parametric models that we receive. So we control the parameters of the product. So we receive the product configuration. And from there, the manufacturing engineers and industrial architects check different options of your process sequences and resources that they can reuse. But these are requirements, so specific requirements that we have for the industrial system. So now more and more we have specific requirements like emissions or rate. Well, we always have rate, cost, and this kind of things, but we have more and more. Okay, so then we develop an application ontology, okay, that is linked to IOF core. So to go into that application ontology, so the application ontology was developed to capture domain knowledge, requirement, and modeling knowledge. So here it was domain knowledge, okay, of how the process, the orbital joint process looks like. Requirement ontology to manage the requirements, and the GeoPBR ontology to manage the modeling knowledge. Okay, all of it integrated using IOF core. So tomorrow we will have a deep dive session of this connectivity and this connectivity in the IOF session. So if you have specific questions on that, tomorrow we will go into specific details with our colleagues. So these three ontologies, well, as I said, they're integrated with IOF core, and there are two main knowledge sources for this application ontology. So what we wanted was to check and reuse existing knowledge from the process, but documented, so explicit knowledge. And out of it, the application ontology was built. So, and we made some checks with the experts about the information that we captured. So this application ontology was pushed into Neo4j to use as structure for the graph database and control the different data flow for the system models and for the simulation models and the visualization. Okay. Then we enriched this ontology with this application ontology with different rules and constraints of the orbital joint process, like precedence constraints with the resources, and all of these rules that are always respected, and that will help us to automatically create architecture options. So the second part of the system integration model is how to automatically generate assembly system alternatives. Okay. So here we made an assumption, so a simplification of the orbital joint process, considering that the orbital joint process, you have always like an upper and a lower process, and then right to left process. So we can check different process sequence alternatives playing at this level of upper, lower, right, and left. And so using the rules and constraints that we predefined in the application ontology, plus a Python script that was helping us to create new architecture alternatives based on the requirements that we were receiving, we created different architecture options that could meet a requirement that was defined. Okay, so going to the requirement management block, so we'll speed a little bit here. So we have a system that is on rack, that is Java-based platform working with OWL models. So this system was receiving requirements. So requirements are text-based, and it was cleaning the information, and so to fill out what were the requirements that the architect, well, the engineer was receiving. And so that then the architect can define the performance requirements. Okay. So it was also following some relationship of how to cascade these top-level industrial requirements into performance requirements, and it has a little loop of how to create, update, review the different requirements that were defined. Okay, and here it provided output as OWL and XLS through the system integration block to integrate the data. So this is the requirements ontology that we use. So model in OWL, and it used the top-level industrial requirements as defined in Airbus. So this is an application level. But later it was based on system requirements, specifications, and all that. Okay, so I think nothing more here. So after the requirement management block, so the architecture definition block. So here you see that there is two different functions. So one is an interaction when an architect defines the system from the beginning, so it models the systems. And the second option, it was when we trigger the automatic generation of architecture options. So from a design requirement, the algorithms were triggered so that we can propose to the architect different architecture alternatives. He can check and then see which ones are the one that he wanted to simulate. So this is using Metagraph version 2. As a tool, but as we said, the approach is tool agnostic, so we could change that. And the supporting meta model is GOPPRE for the model transformation. So we could pass the information from different modeling languages, so that the architect choose whatever was more fitting the method that different architects were choosing. And so all the architecture model were fulfilling the MOFLT approach, so describing the mission, the operation, functional, logical, and physical structure of the system. I think a lot of time. Okay, so this We had a model transformer as well from the architecture model to OWL, so that to allow the connectivity again to Neo4j through a Neo4j API. So we import OWL models into the architecture model by using metagraph options, and we did the other way around as well, transforming those models into OWL models to be fed back to the knowledge graph database. So finally, then the visualization and the verification blocks. So here there are two types of simulations. So the 2D simulations, they were capturing first the design options. Okay, so all the architecture options that they need to run, creating discrete event simulation models based on the architecture that was defined here, running the simulations, and they're making a comparison with the requirements that were defined, so that the visualization block can show to the architect the different alternatives that were regarding the KPIs that we were trying to see. So it's a Python-based platform, and it has connectivity to the system integration block. And integration was made through the ontology. So it was using directly the application ontology to call the different data of different architecture options that were defined before. Then for 3D simulation, we use visual components. We use that for 3D factoring simulation, so to check clashes and to check all the different architecture options put in a 3D environment. And this was this had a little a process a little bit more complex. So we were the simulation model was using an existing layout. We were triggering the import from the ontology to get the data. And in the background, so there was a mapping between the objects in the ontology and the data structure of the visual components of product, process, tasks, and resources. There was a simulation run, so they were using as well objects from a 3D library. So the 3D library had behavior and so parametric and behavior components that we were using. We ran the simulation, and the visualization was enabled through VR or 3D on screen. And just to see how that looked at the end. So this is the prototype. So this is what the final user would see, okay, the industrial architect. So as a first step, he will define the requirements. So here he goes to the on-rack interface. So he uploads the information that he receives, text-based, about the requirements, the top-level industrial requirements that he needs to fulfill. Here you see that the information on the board is processed in the different classes of the requirement ontology that we're using, and then he can edit the information, and here it will refine the requirement to set a specific performance requirement. So as we were saying before, so one performance requirement for example, for a new line, have a minimum value of throughput of 150 aircraft per year. So this triggered the automatic generation of different assembly sequence options, so orbital joint sequence options. In this case, we had 18 different options that we can see here in the graph. And these options there were visualized in Metagraph in different modeling languages that were applying the MOFLT methodology. Okay, here we can update some values, for example, the parameters to define the parametric optimization that we were searching for to simulate. Then we run the simulation. So this was different options, for example, that we want to assess on the learning curve as a parameter for the discrete event. And here are the results for all 18 different architecture options that we're analyzing. And we can see different visualization of all the KPIs like lead time, throughput, overall equipment efficiency, and etc. Okay, and which options are satisfying or not the requirements that were set at the beginning. And finally, so the architect was able to check this information in a 3D environment. So you have just seen how the process information was imported. So it was one architecture at a time. So here he was checking one of the options, the more promising options, and checking the 3D simulation for potential problems in it. Okay. So to conclude, so we have demonstrated a trace space framework that is using state-of-the-art technologies and different ontologies that are proposed in the ecosystem. So its current maturity level assessment is 0.5 in our maturity process. So all tools that we're using these prototypes have APIs that are based on standards, because our purpose is that this framework is transferable also to any other toolset configuration that we can choose in the different maturity levels. So the application ontology was developed, capturing knowledge from the data and controlling the requirement and the modeling knowledge. And there was an automatic design solution generation available as well. So this ensured the semantic integration of the data flow and an ontology-based engineering principles for design automation. We had this discrete event of 3D simulations automatically generated out of the architecture options that were defined. So these reusable parametric models are interesting, an interesting point. So this is a way of how we will apply MBSE method in the industrial system design. And this is just demonstrated for the orbital joint process, but this can be transferable as well to other processes that we have. And that's it. So if you have any additional questions, I'll be
Yep. What do you use for reasoning Becca, because your project doesn't have reasoning?
True. So, well, we use a Python script on top of understanding the rules that we have defined in the graph and acting on that. But do you want to complement?
Yeah, if I may, just clarify something. Because here there are two types of reasoning. So the one in ontology, so we include some query, and the reason is running inside the ontology. Well, the ideal situation would be you include the requirement, you give me the possible solution. But still, we are not that tested. Currently, the reasoning we did is in the graph database. The graph database was constructed based on ontology. The ontology provided like basis and the backbone, the graph. Then we have some rules defined. For example, this process has some essential operations, and then have some optional operations. Then you can choose different from one of them. This will generate different solutions for this process. So this generation process is done with the customized algorithm using Python and querying in the graph database. So this is a kind of knowledge reuse. Basically, the orbital joint process, the properties or the rules are predefined based on the previous similar systems and stored in the graph database. And we use this algorithm to query and reuse this knowledge to generate all the possible combinations of equations and generate new solutions. Then the new solution will be verified.
Right, I have a question. Thank you for the presentation. When you show, in terms of visualization of the scenarios and which constraint is respected or not.
Mm-hmm.
So do you plan to add what, I mean, it's hype now about explainable AI and I mean, through ontology, I think there is a possibility to show the reasoning aspects, how, I mean, when you love the reasoning, so you can show explanations about that. So do you plan to add this in order to let's say, to allow the end user to have more trust because you understand why this requirement is respected or not?
Yeah. So that could be definitely part of the next steps. So this was validated by different final users, and this was one of the questions raised. So how do I, rely on the analysis that was performed in the back? So this is definitely one of the axes. Yeah, and also in terms of the actual visualization, so the ergonomic of the visualization. So it was not the aim of this demonstration per se, but it was also one part that they were mentioning. So it has to be something that they can actually take decision from.
So this is the thumbs up for the LF core?
Well, we'll see the details tomorrow. So I invite you to join the 2 sessions tomorrow. Yeah. And sorry. I just had one last thing that I wanted to pass. So we're hiring. So we have an open position of ontology expert. So if you know about anyone that is interested on joining Airbus, and as an ontology expert, so we have an open position in Toulouse. So feel free to join.
How much? Are you considering delaying your retirement?